Hello and welcome. Eamonn Darcy is my name. I'm the founder and operator of QEQWA, the Quantum Education Center of WA. And I'm so excited to bring you the first lesson of our 10 by 10 minute videos on quantum computing. I'm only going to speak for 10 minutes, so we have an awful lot to get through. And lesson one is about superposition, which is an amazing fundamental force of quantum physics, which we still can't explain, basically. It's still a mystery. Quantum is anything smaller than an atom. So without any further ado, I'm going to start my 10 minutes on my iPad, and let's take it away. Okay, I just want to tell you the scope of quantum computing. Jeff Bezos, the founder of Amazon, of course, says that quantum computing is the future. I am not exaggerating when I say it will change everything. And he's absolutely right. It's going to change mankind far more than the introduction of the internet, because a quantum computer, as you'll soon see, is not just a faster computer, a bigger, faster computer than before. It's totally different. That's like comparing a candle to a flashlight. No matter how much bigger and better you make the candle, it'll never be the same as a torch. So that's what we're talking about here. Again, I just want to get over the impact of quantum computing. When you use an ATM, you're completely safe, because it will literally take the fastest computer on Earth at the moment, which is a digital supercomputer at Oak Ridge at IBM, and it literally does 200 quadrillion operations a second. Super fast, but it would still take it over 1,000 million years to get your PIN. So you're completely safe. But a quantum computer can get your PIN in 6 seconds. 8 minutes, 20 left. Okay, superposition all comes back to 1801 with Professor Thomas Young. And he wanted to find out the fundamental nature of light. So he set up a very basic experiment, which were the two slits that you can, two detectors. The first one has a double slit, and the second one is the back detector screen, which will catch what happens when the light goes through the two slits. Now, his theory, which was sound, was basically, if light is a particle, it will be like firing a machine gun at the front detector that has the two slits. And then you would expect at the back detector, you would expect to see two vertical lines where the bullets have gone through. But if light is a wave, it would react rather like water or sound. Imagine if you're pushing water through the first detector board. What would happen is the water would go through, and then immediately it would start overlapping with the waves. And that's called interference. And with interference, you would get multiple vertical lines at the back, as if these multiple waves are touching the back detector at the same time in various places, with the strongest detection being right in the middle. So he did his experiment, and I've got it up on screen now, and you can see that he did in fact get an interference pattern, which meant light was a wave, and he ran around the laboratory very, very happy, screaming and shouting, "I've worked it out, light is a wave." I've got 6 minutes, 10 seconds left. And indeed, for over 100 years, we did consider that light was a wave. But then we found it was far more complex than that. And what happened was a man called Einstein came along in 1912, and he did an experiment for which he got the Nobel Prize for Physics. and it's called the photoelectric effect. It's actually the way solar panels work today. And I won't go into it, fascinating as it is, but it actually just proved that light was a particle. Now, Einstein said, now, I've witnessed Thomas Young's experiment that proves it's a wave. And, you know, this proves it's a particle. So I'm not quite sure. And this was the beginning of mysteries in the quantum world. And what they did then, something even stranger happened. They got to the stage where they could fire, instead of poor Thomas Young had a little gap in the curtains, but they got to the stage where they could send one photon, which is the unit of light, from a light source. And what they then did was they placed a camera on the slit because they wanted to see what was happening when it went through the slit. So, by the way, not a camera like that. It was a very, very technical, high-speed camera. That's the only graphic I could find. Forgive me for that. Oh my God, we've only got 3 minutes, 10 seconds left. When they put the camera there, an amazing thing happened. At the back detector screen, instead of the interference pattern, they saw what's called a clump pattern. So they saw the machine gun, i.e., amazingly, the wave happening event that gave us the interference pattern immediately disappeared and became a clump. And this was unbelievable. Take the camera away, it's interference. Put the camera there and it's a clump. It was amazing. And what Einstein and many, many others came to the conclusion was that before it was measured or observed, the photon or the quantum particle was in a very strange position of being what we call wave-particle duality. It was a wave, and I'd like to stress that the wave doesn't mean an actual wave like sound and light. It means a wave of probability. You cannot say where the quantum particle is. And this all comes back to the Heisenberg uncertainty principle, which says for a quantum particle, you are not allowed to know its momentum and location at the same time. I've got 1.5 minutes left. So it's not like we haven't got the technology. It's like nature won't let us know where a quantum particle is. Before being observed, it's in this very strange state of being both. And we call that state superposition. And superposition allows us, when we're on the computer, instead of only being able to map or reference to 1 or 0, we can use linear algebra to reference to many, many different locations, literally millions. We can maneuver this to, and we do that using microwaves. So superposition is not 0 and 1, it's 0 and 1 and everything in between, and 0 and 1 at the same time. And all these different areas can be mapped to. And that's why we get an exponential effect from superposition. I've got 15 seconds left. So I just want to tell you about the next free video, which will be coming out within the next 3 or 4 days. And that's on quantum entanglement, which, believe me, is just as exciting. Thank you, everybody. There goes the clock. See you later.